Okay, can everybody see everything? Yeah. Okay. Just pull this closer so my audio quality doesn't turn terrible. So today we will be talking about the non-existence of the Quintic formula. This is like called the Abel-Ruffini theorem. Most of us are probably aware of the quadratic formula. There is a cubic formula, some of you might have seen. And there's also a quartic formula. But it turns out that it's just impossible to find a Quintic formula. And we're going to be almost proving that there's no Quintic formula. There are some details that we will have to omit, and like some assumptions we will have to make. But this is just the main destination of the talk. We will explain why there is no Quintic formula on at least the moral level. Yeah. I will be going decently quickly, so like I guess my advice is not to try to take full notes or anything, and just listen. Okay. I will be looking at the chat for anyone who has any questions, so feel free to ask there. Okay. Cool. So let's start off with the quadratic formula. I'm sure we all know how to solve quadratics, but I guess here's a slightly different from the conventional complete the square method of deriving it. If you have the roots r1 and r2 of the quadratic x squared minus bx plus c, just like note we're using minus because it's far more convenient in many ways. And also we're just going to assume everything is monic. You can easily turn every polynomial into a monic polynomial. So if you have the polynomial, or the quadratic polynomial x squared minus bx plus c with roots r1 and r2, you know by Vieta r1 plus r2 equals b, and we can compute r1 minus r2 squared. Like this is just expressible as like this minus this, and you get b squared minus 4c, which should look familiar because it's a term under the square root. And then you can solve a system r1 plus r2 equals b, r1 minus r2 equals root b squared minus 4c. And now the question is like, which square root do I take? Do I take the positive one, the negative one? Or if the coefficients are non-real, you just have like, it's not very easy to choose a square root to take. But I guess the idea is, no matter which square root you take, your set r1, r2 is going to be the same. Like if you take the other square root, r1 and r2 are going to be swapped. So that's what this side is. Basically, if we change which square root we use, we're fundamentally swapping the roots r1 and r2. And like, all our expressions, r1 plus r2, r1 r2, r1 minus r2 squared, these things stay like mostly the same. They're symmetric in r1 and r2. When we take our square roots, we lose the symmetry, but we have the choice to like choose which square root we want. So yeah, that's why like swapping r1 and r2, we'll swap r1 and r2 in the quadratic formula. I should clarify, when I say formal square root, this is like over C. When you're taking square roots, it's pretty hard to choose. There isn't really a principal square root. You can do this thing called branching, which I won't get into, but basically I'm saying you're picking one value, one square root, and then I'm thinking about like when I swap r1, r2, I'm gonna pick the other square root. Does that make sense? So like this is where you get the symmetry in the quadratic formula. This is why your quadratic formula is able to give you both of the roots of the quadratic. There is a plus or minus square root. Like the square root is responsible for it all. Okay. If there are not any questions, let's go on to the cubic formula. Some of you might have heard of like Cardano's method. This is going to be a slightly different, like just like the quadratic formula method, this is going to be a slightly different way to think about the cubic formula. If you have the cubic x cubed minus e1 x squared plus e2 x minus e3, and note again it's monic and I'm alternating the coefficients, so the signs of the coefficients, so Vietas holds nicely. Now, like, remember in the quadratic case, we looked at R1 plus R2 in the quadratic case. We looked at R1 plus R2 and R1 minus R2. So here we want something like equally symmetric in 3 variables. So we let omega be a primitive third root of unity, and then we look at these 3 quantities. No, we don't. We look at these quantities along with R1 plus R2 plus R3. These follow from Vietas. And the idea is, like, in the quadratic formula, we're able to determine all of these quantities. So can we do it again in the cubic case? And the answer is yes. We consider this quadratic polynomial with roots s1 cubed and s2 cubed. And it turns out, like, f1 and f2 are going to be symmetric in R1, R2, R3. And you can just, like, check this directly. Like, basically, if you look at this expression, R1 plus omega R2 plus omega squared R3, and then you cube it, like, you can scale this inner term by omega, and, like, nothing happens to s1 cubed. So, basically, like, when you rotate your permutation, s1 cubed stays the same and s2 cubed stays the same. And when you swap 2 elements, so, like, rotate your permutation, like R1 goes to R2, goes to R3, goes to R1, s1 cubed, s2 cubed are the same. And then when you, like, swap R1 with R2, you can check that, like, s1 cubed and s2 cubed swap. So basically, like, this set, s1 cubed, s2 cubed, is always the same. So, like, when you look at f1, which is their sum, this is going to be symmetric in the 3 variables R1, R2, R3. When you look at their product, which is, if you look at f2, which is the product of s1 cubed and s2 cubed, this is also symmetric. So this means, like, f1 and f2 are symmetric polynomials in R1, R2, R3. And just, like, some meta thinking, the fundamental theorem of symmetric polynomials tells us we can express them as polynomials in E1, E2, E3. So, and we know what E1, E2, E3 are. So basically, like, meta thinking tells us we are able to compute f1 and f2. And indeed, we may evaluate them by hand. We have f1 equals this and f2 equals this. So, like, when you're solving a cubic, you can evaluate these. And then once you evaluate these, you can, of course, solve the quadratic, find s1 cubed, s2 cubed. And then when you take the cube root, you get s1 and s2. And then you get this system of equations. And just like the R1 plus R2 and R1 minus R2 system, you can pretty easily solve this. Like, when you sum them, you notice you get, like, basically R1, and then you can, like, scale things by appropriate factors of omega, such that you get the other S1 and or you get R1 and R2, or you get R2 and R3. And then this is, like, once you do this, you solve the cubic. It's pretty clean, I think. We won't state the cubic formula because it's rather long. But the point is that, like, this is a method you can use to solve cubics, and it will give you a decently looking expression, like, of the form, I believe you get, like, negative b over 3 plus cube root of, like, something plus square root something plus cube root of something plus square root, like, or minus something. Which is, like, I guess a cubic formula is in similar nature to the quadratic formula. So yeah, it will be given in terms of the symbols plus, minus, times, division, and the nth root, using only the coefficients of the polynomial, and of course, like, some extra constants. A similar method may be used to solve quartics, but I don't want to give the details, like, in the interest of time. But the details are, you can look at, like in quartics, you can look at R1 plus R2 plus R3 plus R4, R1 like minus R2 plus R3 minus R4, R1 plus R2 minus R3 R4. There's something else. Was it this one? Yeah. And you could look at these 4 things, which are pretty symmetric in the 4 variables. and you can like evaluate these 4 things and then solve your system of equations. Okay, are there any questions at this point? Okay, quiet crowd. Okay, let's look at the symmetries here then. Recall that like at some point, like we solve a quadratic and get s1 cubed, s2 cubed, the set. This is all like well defined. Then we take cube roots, but recall we're working over C most of the time, and most numbers have 3 cube roots. So like, why are we allowed to take the cube root of s1? And the answer is like, it doesn't even matter which cube root we take. Like these are the possible cube roots we take, and these are all like fine if we permute the roots of our cubic. So you see a lot of like symmetry in what we're doing, and like in the Quintic formula, when you choose these 4 quantities, there's a lot of symmetry as well. So like the reason you can't get a Quintic formula is like for degrees of 5 and above, you simply lack this symmetry. And to make our discussions about like this type of symmetry and n variables more explicit, we need to use group theory. So, definition. Let G be a set of permutations of x. So like we permute the variables in x. Like commonly x might be like 1, 2, 3, in which case G is like the set of 6 permutations of, or a set, I guess, a subset of the 6 permutations of 1, 2, 3. You could also like try permuting, like often we will be permuting the roots of a polynomial, as we have done. So we say that G is a group of permutations of x if these three things hold. The identity is in G. Identity is just the permutation fixing everything. For all f in G, the inverse of f is in G. And for all fg in G, the composition is in G. And you might notice that if, to those of you who know group theory, we're basically like defining a group on a set of permutations with group operation composition. So, like, I guess like S3, the symmetric group of size 3, which is like the 6 permutations of 1, 2, 3, is a group. And then you have like the alternating subgroup foreshadowing, A3, which is, I believe, you have like, let me think. You have the identity, you have like 1, 2, swap 1, 3, what is this? Oh, this is just a 3 cycle, yeah, okay, 1, 2, 3, 1, 3, 2. Here we're using cycle notation. Do people know how this works? Like when I say 1, 2, 3, like I say 1 goes to 2, goes to 3, goes to 1. And here we say 1 goes to 3, goes to 2, goes to 1. Is that fine? Okay. So, our next definition, given a group of permutations G of x, and for all elements x of x, we say the stabilizer of x is a set of G such that G of x fixes, or such that G fixes x. So like, if we look at the element x equals 1 in A3, like the stabilizer of 1 in A3 is simply the identity. And I guess like stabilizer in S3 of 1 is identity, and there's also like swapping 2, 3. Is that all? Yeah, okay. Now for all x and x, we say the orbit of x is a set of all elements of the form G of x. This is as G ranges over G. So basically, like, this is the possible things you can send x to. So like stabilizer, orbit A3x is going to be 1, 2, 3, because there are permutations sending 1 to itself, sending 1 to 2, sending 1 to 3. And same thing with S3x. So this definition of orbit and this definition of stabilizer are going to be rather important. I just want to like linger here for a moment and make sure nobody has any questions, because this is going to come up quite a bit. So any questions, feel free to ask. Okay, I guess we will move on. So let's like analyze the symmetries to the cubic formula using our orbit and stabilizer. So let X be the set of polynomials in 3 variables, and S3 the symmetric group, so the group of permutations on R1, R2, R3. I guess to be more explicit, this is like the set we're acting on. For each of the following polynomials, describe the orbit and stabilizer. So this has been a quiet crowd, but does anybody want to answer these questions? Then you have the polynomial R1. What is its orbit? Okay, so the orbit of A1, or of R1, is R1, R2, R3. Like, this is basically the example I gave earlier. What is S3 of 1 in the set 1, 2, 3? It can go to everything. And then similarly, the stabilizer of R1 is going to be, I guess, identity on the thing swapping 2, 3, right? Now if you look at this quantity, what is S3 of R1 plus omega R2 plus omega squared R3? So what fixes this? And I don't believe anything fixes this, so this should just be the identity. No, that's the stabilizer. Oh, my bad. So stabilizer of this is the identity. This thing can just go to everything, right? So like R1 plus omega R2 plus omega squared R3 dot dot dot, you get all 6 permutations. Okay. But when you cube it, recall that we said like when you cube this quantity you can scale it by omega. So you're actually like allowed to shift the variables. So basically your possible values are R1 plus omega R2 plus omega squared. There should be superscript. R3 cubed, and then this thing with 2 variables swapped. And then your stabilizer I wrote in the subscript again. Your stabilizer is the identity and like anything that rotates the variables. And then you have S3 of this, dot dot dot. There are like only really 2 possible values of this, right? Like when you swap 2 variables, you like negate it. So like negative of itself. And the stabilizer, everything that fixes it, should just be identity 1, 2, 3, 1, 3, 2. Okay. So like to summarize our findings, we have this slide. Is this fine with everyone? Okay. So, you might notice from the details on the previous slide, we have the following conjecture. For X is set and G a finite group of permutations on X. For every X in X, the size of the stabilizer times the size of the orbit equals the size of the group itself. So if we go back here, you have 2 times 3 equals 6, 1 times 6 is 6, here you have 2 times 3 is 6 yet again, 2 times 3 is 6. No, these are both 3 times 2. Right. So this seemed likely for this conjecture to be true, and it is true. It's called the orbit stabilizer theorem. And like a proof of this takes on the following form. You're basically just like, when you want to prove the size of some set is equal to the size of the products of two sets, it seems likely we're just going to construct a bijection between the two. And the bijection is like as follows. Basically, like for each possible value of x, like there are going to be possibly the same number of permutations with x in that slot. So like we're just gonna like have a map from G to the orbit times the stabilizer. So like just a reminder, this is like things fixing x, and this is like where x can go. So like, of course, sigma of x for every permutation, or for every permutation sigma is a possible thing in the orbit. And then this is like going to be one such stabilizer. Right. So like the details might be, if you want to check that this map is a bijection, like basically what we're saying is we're applying our permutation and then we're going to swap x and sigma x. So if you want to check that this is an injection, or if you want to check that this is a bijection, you need to check that this is like an injective map and then a surjective map. So like surjection should be easy, right? Like for every sigma of x, for every pair of like y, and then some permutation tau fixing x, you can go backwards to like y times, or first you apply tau, and then you wait, hold on. Oh, tau is not a permutation fixing. Oh wait, it is, my bad. So tau is a permutation of fixing x, and we want to go backwards in time to find a permutation in G that sends values to sigma of x. So I guess we have like tau is xy compose sigma. So we just like go backwards and take sigma is xy inverse, which is just xy times tau. So that's surjectivity. For injectivity, like it's practically the same thing, I think. Like if you have two pairs, y of tau, y1 of tau, y2 of tau 2, these both go backwards to, or if these two are the same, like if f of sigma 1, or if sigma 1 and sigma 2 both map to tau and, or y and tau, you get like sigma 1 and sigma 2 are both xy compose tau. Like basically we've constructed the inverse of this map, which is like this. So this map is a bijection. Does that make sense? So like the idea is like when you swap x with anything, you have the same number of things like fixing that value in your group of permutations. Okay. Let's move on. Group actions. So now we're just going to like generalize from group of permutations to more abstract groups. So our goal here is like, we start with an abstract group G and turn it into a set of permutations. So if you have G a group and X a set, an action of G on X is a binary operation, such that for all X and X we will have 1 times X equals X. So like the identity is like an identity, basically. Like the identity of the group is the identity permutation. And for all FG and X, we have like, basically we just have associativity. And not that it's like allowed for G times X to equal X for G not equal to 1. 1 is not necessarily our only identity. So for convenience, we will usually omit the time symbol and also the parentheses because we know already it's associative. So basically each G in G corresponds to a map X to X. We just send each element X to G of X. And each such map can be easily checked to be a permutation. A permutation is basically a bijection, so again we check injectivity, surjectivity. So if G equals GB, then you can multiply both sides on the left by G inverse, and then this is just gonna give you A equals B. And for surjectivity, we can just like take the inverse, and that will work. Does that make sense? Okay, moving on. We can repeat the definitions of orbit and stabilizer in this context. So like if a group G acts on X, then the orbit of X is like the set of possible places X can go under the group action. And then the stabilizer is like all groups in the, like all groups in G, or all things in G that fix X. So this is like a very familiar definition. Should just make sense, I hope. And then, like the other definition of orbit and stabilizer, we get the more general orbit. Wait, where did the orbit stabilizer theorem go? Okay, never mind. There is the orbit stabilizer theorem for all G, X and X. Size of G equals size of GX times size of stabilizer of X. Okay. Oh, maybe, okay, I think I jumped too fast forward in time. Whatever. So here's an example. We're gonna look at the rotational symmetries of a cube, with multiplication being composition of the symmetry. So like, we're gonna have the 4 rotations, and then like their respective reflections. You might have like your base square ABCD, and then you have like ABCD, etc. And you also have ABCD. So we want to find the orbit and stabilizer of a point X in each of the following. Right. Okay, I misread my own slide. We're doing a cube and not a square. Okay, so there's some number of rotations, reflections of this cube, and we want to find the orbit and stabilizer of a point X in each set, where we have a set of faces of the cube, set of edges of the cube, set of vertices of the cube. So let's like think about the set of faces of the cube. Like basically like, we're gonna call this face X. So the stabilizer of X is going to be like any rotation, any reflection, like fixing X, right? So you can like rotate your cube, and I think you can also like reflect your cube. Oh, we're only dealing with rotational symmetry, so that's nice. So we're only rotating our cube. So this should have like size 4, I believe. And then the orbit of X. So like orbit of X. It's just going to be all 6 faces. Since you can obviously just like rotate your face onto any face you want. And similarly for the edges, like there are 12 edges, and the number of things like fixing, the number of rotations fixing an edge of a cube should just be 2. You have like the original thing, and then you can just like, I guess, invert around this edge So I guess here you get like, here you get stabilizer has size 2, orbit has size 12, and then set of vertices of a cube. Your stabilizer should have set 3, should have size 3 because there are 3 neighboring faces that you need to preserve. You can rotate them in 3 ways. And then GX is 8. There are 8 possible vertices of a cube you can go to. So yeah. And I guess this demonstrates that yet again we do have orbit stabilizer theorem. And the proof is like mostly analogous. You just like take representatives and show that things behave. So like the details are all here. I'll post the slides later if you want to go through them, but it's just basically the same, except like slightly more rigorous than the previous orbit stabilizer. And we do have this corollary that's like pretty nice to use. Like the size of the orbit always divides the size of the group itself. Okay. So like, we can try to use this on like, if we consider polynomials in 4 variables, and the orbit is like all polynomials we obtain by permuting the variables. So like basically orbit is like, we're using the group S4 to permute R1, R2, R3, R4. So for which positive integers n can we find the polynomial f whose orbit has size n? And first note that like S4 has size 24. So we know S4f by orbit stabilizer divides 24. So our candidates are going to be 1, 2, 3, 4, 6, 8, 12. And it turns out we can in fact construct these. And I will say like being able to construct all of these is like kind of an accident. In particular, for polynomials in 5 variables, it will be hard to construct everything. I don't think it's possible. This is just like an accident. Just like I will say like the fact that there's a Quintic formula or there is no Quintic formula is not that surprising. What is surprising is that there is a quartic formula, which is again like an accident. So like because of this coincidence we can find the quartic formula, and this will fail for Quintic formula. Before we move on, is there any question about orbit stabilizer? Okay. So now we will move on to a discussion about characters of groups. So what is a character? Well, a character is a map from a group to the set of non-zero complex numbers, such that for all g1, g2, like we have chi of g1, g2 equals chi of g1 times chi of g2. So it's a multiplicative map. And let chi be a character of g, we're going to define the kernel of the character to be the set of g that map to 1. So like an example of a character is like the trivial character, the identity, with kernel chi just equal to g itself. Okay. Here's a fact. For any character chi of g, the kernel of chi is a subgroup of g. And like, why is this true? Well, first, like, you can just check the axioms of a group. Like, the identity, chi of identity, we usually denote, like, the identity as e. So, like, chi of e squared equals chi of e. And this is, like, also chi of e. So chi of e is 1. So like our identity is in the group. Like if g is in the kernel, then like chi of g inverse is 1 over chi of g, which is 1. So like the inverse of every element in the kernel is in the kernel. And then for g and h in kernel, we have chi of gh is chi of g, chi of h is 1. So like your the kernel is closed under multiplication. So this verifies like the 3 group axioms. So the kernel of every character is a subgroup. Okay, so like, as an example, okay, now we're going to consider the symmetries of the square. And there are 4 characters, and we want to find them. So first of all, let's like look at one possible symmetry in the square, and that's rotation. I mean, that's reflection across a horizontal axis. So we're gonna call this one H. Note that applying H twice gets you back where you started. So H squared equals E. Oh, this means, well, first of all, chi of E is like 1, as we have checked already on the previous slide. So we now know chi of H squared is 1. So chi of H is like either 1 or negative 1. Now, on the other hand, you have a rotation, right, in the group of symmetries. So we're going to call this R. One can check that RH is E. So this means chi of R squared is like 1 over chi of H squared, which is 1. So chi of R is in plus or minus 1. And now note that H and R like generate the entire group. Like everything in the group can be obtained by some combination of reflection and rotation. And we can check that like these 2 choices allow us to determine everything. So there are 4 possible characters and we can describe them. So yeah, this slide. Now let's think about characters from polynomials, trying to like navigate back to the path we were originally on talking about polynomials. Recall Sn is a group of permutations in n variables, the symmetric group. We have this function delta on n variables that is just the product of all Ri minus Rj. Recall in our discussion of orbit stabilizer of polynomial, or just orbit stabilizer of permutations in polynomials of cubic, I believe, that we have seen like delta on n equals 3. So note that this thing is like here W is a thing in Sn. Note that like when you take W delta, like basically like every single term Ri minus Rj, it's just going to be like plus or minus of like what it originally is. So this means like W delta is like plus or minus. Should this say delta? I think it should say delta. Peak. Yeah, okay. It should say delta. So W delta is just going to be like plus or minus delta. So this means your character is always going to equal plus or minus 1. And now to show this is a character, we just want to show like multiplicativity. And this is like not too hard. If you have like VW in Sn, like epsilon of VW is going to be VW delta over delta. And we can write this as VW delta over W delta times W delta over delta, which is epsilon of this is epsilon of E and epsilon of W. So this checks that this is a character. Does that make sense? Okay. That's the slide. Here's another example. This is yet again something we have seen before. Show that the stabilizer of A cubed in S3 is a group with 3 elements. I think we have done this already. So, like basically when you cube, you're allowed to rotate. So your group R3 is going to be identity 1, 2, 3, 1, 3, 2. And now, we say that G is a character on A3. And yet again, we can compute like alpha of GH. Or first of all, like identity is like 1, right? Alpha of GH. Actually, we don't need to check this, I think. We can just directly check that this is a character. And you can do like the same proof as before. A is GHA over HA times HA over A, which is alpha of G, alpha of H. So it's a character of A3. Does that make sense? Okay. Yeah, this is another example. I guess I will. It's basically the same. I'll skip it for the sake of time. But, like, our results can be generalized into this, like, proposition, which I encourage you to try to remember, because this is going to be pretty key later on in this presentation. So if you have a non-zero polynomial and a positive integer k, then, like, for all g in the stabilizer of f to the k, you have, like, this for some scalar chi of g in the non-zero complex numbers, and this is going to be root of unity. Like, basically, like, g, when you're acting on a polynomial, has the following properties. Like, g of f plus g is g of f plus g of g, and g of fg fg is g of f times g of g. And you can just like manually check these in your mind or something. So yeah, basically gf raised to the k is just going to be g acting on f to the k, and since we're given g is in the stabilizer, this is f to the k. So when two things have equal kth powers, their ratio is the kth root of unity. And chi is also going to just be a character, and you can check identity, of course, goes to 1. And for all gh, you have this following computation that we've already done twice. Does that make sense? Okay. Now let's start talking about permutations. So we've said symmetric group a few times. This is the group of all permutations on n variables Sn. Now, recall we have a character epsilon from Sn to plus or minus 1, which is just like the ratio of like this thing over what it should be. So the alternating group An is defined as a subgroup of permutations for which epsilon of w equals 1. And like you can think of permutations in this alternating subgroup as like even permutations. Like permutations not in here are odd, and like basically every permutation can be achieved by like swapping things over and over via bubble sort, and like every permutation in the alternating subgroup requires an even number of swaps, and everything not in it requires an odd number of swaps. So like I guess by swapping like any two elements R1, R2, you have like a bijection between An and Sn minus An. So in particular, like the size of An is half the size of Sn. Okay. So like we saw, like A3 has size 3, for example. And now we have built characters alpha and beta from A3 to like, basically we have built characters on A3 and A4 that are pretty complicated, I guess. The character beta, or I guess like we have technically built this one. I skipped it. But basically we can. And the idea is like, for constructing beta is you use these three polynomials, which are like three things symmetric in R1, R2, R3, R4, which is like a bit surprising. This is kind of an accident that you can construct three things that are symmetric in 4 variables. Yeah, and this is like, as I said, an accident. It's hard to generalize. We can't really do anything similar to construct a non-trivial character on A5. So like that's going to be like our next objective. Prove that characters of A5 are usually trivial. And to do this, we're going to define conjugacy classes. So for two groups G1, G2, and G, we say G1 is conjugate to G2 if for some H we have G1 equals H, G2, H inverse. And conjugacy is an equivalence relation. So like you split G into equivalence classes that we're going to call conjugacy classes. And you can note that if G1 and G2 are conjugate and chi is a character, then chi acts the same on all elements of a conjugacy class. And that way you check this is like, or hold on, this is not, or yeah, I think this is true. Yeah, okay. Yeah, so chi acts the same on all elements of a conjugacy class. And the way you check this is like, in this definition, chi of G1 is chi of H, chi of G2, chi of H inverse. And multiplication over C is like commutative, unlike groups. So like we're happy, you should just like die, and you get chi of G2. Okay, so what are conjugacy classes like actually doing? What is the point of this definition? The point is that like conjugacy classes preserve cycle structure. So for example, if you have a permutation 1, 2, 3, 4, 5, its conjugates are exactly the permutations of the form like A, B, C, and D, E. And this is not that hard to check. You just like use this and look at where H sends, like what H sends to 1, 2, 3, 4, 5, and see where they go. Okay. So let's talk about characters of our symmetric group. I contend for all n greater than or equal to 2, the only characters of Sn are the trivial character and the epsilon we saw earlier, that is like plus or minus 1. So a transposition is going to be a permutation. It's basically a swap. You take two elements, you swap them, and you fix the other n minus 2. So first we know to all transpositions, like they are the same cycle structure. So they form a conjugacy class, and they therefore have the same character. Now, since t squared equals e, you know chi of t is always plus or minus 1. Basically, like either chi of every transposition is 1, or chi of every transposition is negative 1. Now, via bubble sort, basically all permutations can be constructed as a product of transpositions. Like for example, the permutation 1, 2, 3 is a product of 1, 2, and 2, 3. And so now there are two cases. In the first case, if chi of t equals 1, every permutation is like a product of 1s. So like chi is just the trivial character. Now if chi of t is negative 1, we can check that chi of t is always equal to epsilon of t. And since every permutation is like expressible as a product of transpositions, this will suffice. So these are your only two characters. Does that make sense? Okay. Now, slightly more interesting, characters of the alternating group. We want to show for n greater than or equal to 5, the only character of an is a trivial character. Now we recall we have non-trivial characters for A3 and A4. Those are responsible for the cubic and quartic formulas. For n greater than or equal to 5, there will not be any trivial non-trivial character. So the only character is identity, or is the one character. So like transpositions are not in an, but what are in an are 3 cycles. So instead of building permutations for transpositions, we will instead build them from 3 cycles. What I mean by 3 cycle is you take 3 elements I, j, k, and then like everything else you just send to itself. So it's like a transposition but with 3 things. So it's easy to check every 3 cycle is in an. And now the 2 key steps are as follows. First, we show that every element in an can be expressed as a product of 3 cycles. And 2, we will show that chi of every 3 cycle equals 1. So for the first lemma, we can proceed via induction on n, with base case n equals 3, like obvious. So anyway, for some permutation sigma of an in the inductive step, if sigma of n equals n, then sigma just already corresponds with the permutation in 8n minus 1. So by the inductive hypothesis, we can generate it with 3 cycles. If it's not equal to n, we just like compose another 3 cycle to make it equal to n. So we take some tau with tau sigma of n equals n. Then tau sigma is generated by 3 cycles. Tau inverse is a 3 cycle. So tau inverse tau sigma equals sigma is generated by 3 cycles. Does that make sense? Any questions? Okay. Second lemma. Chi of any 3 cycle equals 1. So if you take a 3 cycle and you apply it 3 times, you get back to yourself. So c cubed is the identity, therefore chi of c cubed equals 1. So now we have already narrowed the possible values of chi to the third roots of unity. But note for any 3 cycle that it is conjugate to its own inverse, because like ijk, ikj, they have the same cycle structure, right? This like looks like I should be j, k, j, which is the inverse. Alright, I guess I do check this fact, but anyway. Or, actually, no, this is important, my bad. The important part is you need 2 distinct things to show that your cycle structure is preserved. So, and this is because we're like, okay, we're no longer working on SN, so we can't just get everything for free. We do need to show things behave via our 2 cycles. So, you can check that ijk and ikj are conjugates in AN using T1, T2. And then from here, it follows that chi of C is equal to chi of C inverse. And then because C and C inverse are in the same conjugacy class. And then combining this with C as a root of unity, a third root of unity, it will give chi of C equals to 1. Does that make sense? Okay. I do believe, like, hold on. I think we need, is this true? Yeah, okay. So you do need its own inverse on the left side. Like the idea of like needing T1, T2 here, instead of just sticking with JK, is you need it to be, since we're working in AN, you need the thing here and here to be even, like to be in AN. So you do need another 2 cycle to make this up. And this is why you need n greater than or equal to 5. For n less than 5, this doesn't actually happen. Like, you don't have enough freedom to pick T1 and T2. Does that make sense? Okay. So, combining these two, we prove our proposition. The only character of AN is the trivial one. And then, from here, we can prove that there is no Quintic formula. So, we're going to let L be the field of formal rational functions in the variables R1, R2, R3, R4, R5. We're going to start with this Quintic in the form we have discussed prior. And then we're going to prove the following slightly weaker theorem. Suppose we compute a sequence of elements of L, starting with our coefficients, and we apply plus minus times division in the nth root. We will insist, this is the weak part, we insist every time we apply the nth root, the output still lies in L. So like every time we take the nth root, we're still allowed to express this thing in terms of R1, R2, R3, R5, R4, R5 as a rational function. Then I claim we never obtain R1, R2, R3, R4, R5. So basically, like, by composing these operations, we never get the roots of the polynomial. And this will prove that no Quintic formula exists of a desirable form. Okay, so how we do this. Let F be the field of functions in L that are fixed by the alternating group. So we start off with the elements E1, E2, E5, which are obviously in A5. And we're trying to reach R1, or that are obviously fixed by A5, so in F. And we're trying to reach the roots, which are not in F. So basically what we will show is plus minus times division, and the nth root cannot get us out of F. So first, it is easy to check that if you have 2 polynomials in F, subtypo. If you have 2 polynomials in F, F plus G, like, if F and G are fixed by A5, F plus G is also fixed by A5. F minus G is also fixed by A5, just the 4 operations cannot allow you to break symmetry in any way. So the only key step that remains is when you take an nth root, you are still in F. Now, why is this true? Note, of course, that this is not true for quartics, cubics, and quadratics. Like, taking nth roots in the quadratic formula, taking the square root is how you break symmetry. In the cubic formula, that's how you break symmetry, taking the cube root, and so on. So, why is it that for degrees 5 and above, when you take an nth root, you stay, like, fixed by A5? Recall this following result that I told you to remember. If you have a polynomial, and k a positive integer, where k is our n here. Oops. K is our n here. If you have something in the stabilizer of f to the k, then chi, where you have chi is gf over f. So chi is gf over f is a character. And here recall we have like gf to the k over f to the k equals 1, and this is a character, is what the proposition is saying. So it follows that w times the nth root of f over the nth root of f is a character of A5. Now hold on a second. The only character of A5 is a trivial character, so chi is just 1. So we have w times the nth root of f equals the nth root of f for all w in A5. And it follows that the nth root of f is fixed by A5. Does that make sense? So like this is like the convergence point of the lecture. You have our discussion on characters, and you have our discussion on like our characters of like polynomials, and then like characters of A5 or AN. Obviously, everything we've said so far generalizes to n greater than or equal to 5. And so yeah, when you're working in quintics, taking an nth root will not change the fact that your expressions are fixed by A5. And so combining these, like we have shown, every expression we can get is fixed by the alternating subgroup, and our roots are not fixed by that alternating subgroup, so we can never express them. QED. Okay, are there any questions? I guess I will like touch up a little bit on this line over here. This slightly dubious line. Basically we've already shown that we have nothing that looks remotely like our quadratic formula. B plus or minus root b squared minus 4c over 2. Nothing like her cubic formula. Etc. Because like in these formulas, every time we apply the nth root, we're still in L. Basically, you can check this. But what if we do something more pathological that throws you outside of L? Then it gets slightly more tricky. What you have to do instead, and the proof of this, stronger Abel-Ruffini theorem, just like there is no expression for R1, etc. in terms of the coefficients with these operators, is beyond the scope of the talk. It will simply require too many prerequisites and like theory, background theory to build up. But basically like the main idea is instead of playing around with this one field L of rational functions in R1, R2, R3, R4, R5, we build a sequence of field extensions where like we make her field slightly larger every time we take an nth root, and then we can show each field extension behaves. And basically, like, in the end, things are still fixed by AN, so you cannot get R1. This is just, like, a sketch. Like, we do need, like, field theory to explain why things happen, and we need Galois theory to explain why the extensions are nice. So yeah. This is, like, not as important. What's more important is that we have concretely proven this weaker theorem. Okay. There are no questions. I guess like here, thanks. This lecture was based on an advanced seminar by David Spire. And of course, thanks to Raymond for basically allowing me to skip all of the group theory and permutation prerequisites. Okay. If there are no questions, then I guess thanks for attending, and I will pass the baton to, like, I believe the physics challenge thing that's happening next.